Hey everyone, back to a new awesome video, and today we're going to continue with our series about electricity and magnetism. Today we're going to start to work with charge distributions. We will first set up our systems and introduce some notions such as charge density. Then we will solve a general electric field calculation for a system of a charge distribution, and finally we will summarize what the steps that have to be taken are in general to solve these problems. So let's start. Alright, imagine we have a charge distribution over here, and we want to know what the electric field is at a point P, for example, right around here. We know that if all of this is charged, there's going to be a lot of small points, little elements of charge, delta Q, that will end up being dQs, are going to cause an electric field on this point. There's going to be lots of little elements. In fact, we are going to break all of our system in small cubes of elements that are going to be our charge elements. Great. Now we will need to number or in some way label all of these little small elements, and we are going to do so by putting the numbers. Continue doing so, and then we know by the principle of superposition that E at P it's going to be equal to E at 1, E from 1 at P,
plus E from 2 at P, plus
that is going to be a quasi-infinite sum. Not infinite because our mass element, our delta Q is not infinitesimal, but it's going to be quasi-infinite. Great. Now this seems pretty much as an integral, and indeed it is what's going to be in the end. It's an integral sum. But we will leave that to the next segment. However, we will need to define some quantities before being able to do that. In general, a very interesting quantity is the charge density. That is a relationship between the charge element and the space element, because we are not going to be able to integrate over charge. To integrate over charge, we are going to have to find a conversion between the charge element and the space element so that we can integrate over space. In general, we define dq over dB, if we are talking in 3 dimensions, to be rho as the 3-dimensional charge density. We defined dq over dA if we are talking in 2 dimensions as sigma. This is the superficial charge density, and we defined dq over ds as lambda, that is the linear charge density. Now, with all these notions, we are prepared to carry out a general calculation of the electric field from a charge distribution. Great, now let's carry out our calculation. Recall, we defined these small elements as delta Q, and now we're going to put in general label I on them. We said that all of these small elements form the total charge, and we are going to go from this delta Qi to dq's, to differential elements. In that way, this is going to go so that the total charge is going to be, in this case, the triple integral of dq over the charge distribution. Now that we have this, recall that a little element of electric field, the E, it's going to be the same thing as always, but for a little element of charge over r squared times r hat. Now, we would like to carry out an integration over the volume. So it's an integration over our sphere or globe of charge, and that is going to be an integration again over our globe of charge. However, we do not really know what integrating in charge really is, and for that we got the expressions we found earlier for charge density. Recall that dq equals rho dB. Therefore, we are going to have that this is equal to the triple integral over space of k rho r squared r hat dB. However, this is still kind of an abstract expression because we do not really know what this r squared and this r hat mean, and we need to get a coordinate system for it to make sense. So we're going to have our coordinate system over here with our origin and our point our point P. It's going to be a point, and then we need to define some unit vectors. We're going to have RP, and we're going to define, for example, RQ, which is the one we are really going to be integrate to. We're going to move this RQ all over our blob of charge. Alright, now this expression for the electric field is not really useful. A better expression to do this is to take the definition of the unit vector and put it into our equation so that we have r cubed r dB. And remember, this is going to be the vector pointing from the charge to our vector rp, to our point rp. So we are going to have this vector rqp, and by our vector triangle that is manifest here, we can see that rp equals rq plus rqp. Therefore, we are going to define, this is the important vector, so we are going to find rqp equals to rp minus rq. Now we are ready to input this into our equation. This is going to be the triple integral over q rho. Now the magnitude cubed of this. I'm going to drop this q so that it's clear this is the one we are integrating, and this is a constant because we are not going to integrate in the point P. We're just going to integrate in the q so that we integrate over the charge distribution. So this is going to be rp minus r times rp minus r dB. And this in general is the integral you would have to solve to find the electric field at the point P made by these charge distributions. However, this integral is not easily solvable. we will need to take care and use symmetries and try to find different tricks to solve this integral, because if not, it's really hard. That's why in the next video we are going to introduce Gauss' law, a very important tool that will help us analyze these systems in a much more simple manner. Alright, let's try to understand the methodology that needs to be taken in general to carry out this analysis. Even though we're not going to do it in this course a lot, differential analysis is a very important tool, and sometimes with charge distributions, Gauss' law fails and you need to use this more orthodox method. First of all, you need to divide into little dq. Divide into dq's. Then you need to find the expression for dq in terms of the volume elements. You need to rewrite dq. You can have the lambda, the linear charge distribution, ds, the superficial charge distribution, which is a sigma dA, or the volume distribution, which is a rho times dB. These are just conventions and you can really use any letter you like, but whatever. Then the next step is to find an appropriate coordinate system. So find a chord system. Then you need to express dE at the point P in terms of variables that you can integrate. That means that you need to rewrite dq in terms of this volume or area or line elements, so that you can integrate in them. And also you need to write all the other variables in your systems as terms consisting on constants or variables that you can't integrate. For example, on the last segment we needed to define the r cubed we had in terms of the position of the point P, we were asking the electric field too, and the position of each of the little charge elements. R of P was constant and the R of Q was something that was changing. Therefore, it is very important to express everything in terms of those things so that everything works out. So we need to express dE in terms of integral variables. And finally, the last step is to do the integral. Sometimes we will need to exploit some symmetries of the system, because if not, in general, it's going to be very difficult to calculate the electric field. However, Gauss' law will be there to help us and we will use it most of the times. In case there is no symmetries that you can exploit, you can just put this integral into a computer and hope it has the enough computational power to handle it and solve it correctly. That is all for today. I hope you correctly understood how to deal with charge distributions and this more orthodox method of differential analysis, but really useful all throughout physics. Next time we will introduce Gauss' law and we will find more elegant methods to find this electric field. However, this doesn't always work and we have this differential analysis method to help us out. I hope you liked it, and any doubts left you may ask them in the comment section and I'll try to answer them in the best way I can. Remember to like the video if it was the case, press the subscribe button, the bell, and follow us on social media so that you don't miss any of the new videos. See you another day with more Physicawesome!